finally, here's a 5 by 5 example that we will compute, that will solve using this simpler method. The only thing we're not going to do, we're not going to compute eigenvalues. They are given to us. Someone gave us this matrix and told us these are the eigenvalues. When they tell us that these are the eigenvalues of the matrix, we can check that. Yeah, we can check that A minus 2 times the identity times A minus 1 times the identity. Let's be very exaggerated here. We can check that these to the power 4 give us the zero matrix. So there are no other eigenvalues. No, doesn't matter if we are working on the field of reals or complex numbers. So we were given the eigenvalues, and now we want to find the Jordan basis. Start with lambda equal to 2. So we define our nilpotent matrix to be, so we're just taking 2 off the diagonal and keeping the rest the same. And we know that n to the 5, that this, we know that this matrix restricted to the eigenspace, so we know restricted to the generalized eigenspace corresponding to lambda equal 2 will be nilpotent, and that's actually the definition of the generalized eigenspace. Generalized eigenspace will be the set of solutions to this equation. So we solved that equation, so here's this dot 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 here indicating there's actually a lot of work from here to here, and then we get a two-dimensional set of solutions, and this is a basis. This is a basis we get when we actually solve the system. And so what we do? Well, pick one of them, pick this one, then compute its thread. We start with this one, we apply n, then we apply n again. So this is very similar to the quick and dirty method. Actually, we just picked one vector from the subspace, from the concerned subspace. And we just apply n to it, and then we apply n again, we get 0, and we can stop. We can stop, because we have a single thread. Let's check the definition. We have a single thread. The tip is, of course, linearly independent, because a family with only one vector is always linearly independent, unless that vector is 0, and this collection of threads is a very simple collection. It has only one thread in it, so we can stop, actually. We found the Jordan basis. Jordan basis for what? For the operator T restricted to this subspace. This is a two-dimensional subspace. We know that because when we solved this equation, we got a two-dimensional set of solutions spanned by these two vectors here. So we're done. We're done with lambda equal 2. We can move forward to lambda equal 1. For n lambda equal 1, we have, or I have to fix this, we have a different matrix here. So we have A minus the identity. So here we have 0, 0, 2, minus 2, and minus 4. And then we keep proceeding the same way. We compute this matrix to the 5th power. We solve the equation n to the 5th times x equals 0. So we find what the solutions are. We find a general formula for the solutions, and we find that this is a basis for the solutions. Okay? So this is a basis for the generalized eigenspace corresponding to eigenvalue 1. So how do we do this? Well, let's compute the threads. Take this vector here and compute its thread. So we have the vector, we apply n, we get another vector, we apply n again, we get 0. So we have two vectors. Well, okay, two vectors. Let's see what happens with the other vector in the basis. So this was actually unfortunate. So let's try now the next vector. So the next vector, we put it here, we apply n, so we multiply this vector. This is a column vector, remember, we multiply it from the left by n. When we multiply by n, we get this. Now when we multiply this by n, we get this. And then when we multiply this by n, we get 0. So what do we have? We have one thread here with 3 vectors, closed thread. And we have another thread here with 2 vectors, also closed thread. What do we want to do with this? Actually, I don't want to follow any specific procedure. Let me just ad hoc decide I want to completely ignore the existence of this thread, And I'm happy with this one alone. This thread has 3 vectors. It's linearly independent here, so because there's only one thread. So, and we know that inside each thread, that we know already, any family of vectors of this type where if they are all non-zero and such that n to the k plus 1 applied to v equals 0, any thread of this type, we know it's linearly independent. So these 3 vectors, they are linearly independent. So we know already it is a Jordan basis. We don't need to do anything else. We found a Jordan basis. So this is just a different version of the quick and dirty method where we can actually play with things in a more flexible way. And we decided to throw away this thread and so we found the 2 threads, one for the eigenvalue 2, one for the eigenvalue 1, and now we just write these vectors. So I'm writing these vectors here and here and here, and I'm bringing the vectors that we found before, these 2 vectors. Let's change color because it's a mess. So these 2 vectors that we found before, which are in a thread like this, we write these 2 vectors. This one, we put it here. This one, we put it here. And we get exactly what we had expected. We get a Jordan block for the eigenvalue 2, a Jordan block for the eigenvalue 1. So this illustrates how we apply this method in this case here.